Dear student, in this lecture, I shall discuss the topics which are quantum mechanical operator, means what is an operator, eigenfunction and eigenvalues, linear and non-linear operator, multiplication of operators, commutator operator, and Hermitian operator and its two theorem. So let us discuss one by one. So our first topic is what is an operator. The what is operator? It is the mathematical rule which changes one function to another function. More accurately, it is the mathematical rule which changes one well-behaved function to another well-behaved function. For example, suppose derivative with respect to x, that is ddx of x square equal to twice x, right? That means this ddx changes this function x square to a new function twice x. Therefore, this mathematical rule, this is an operator. This is an operator because this operator changes this function to a new function, and this function is called operand. Operand. That is, it is the mathematical rule which changes one function to another function. So we can write what is operator. Operator will be a function. Will be a function gives another well function. Another well behaved function. So this is the simple concept of an operator. That is, it changes one function to another function. The next is eigenfunction and eigenvalue. Eigenfunction and eigenvalue. For example, let us take the example of derivatives of x, that is derivative with respect to x. ddx of e to the power x is equal to e to the power x. Again, derivative of ddx of e to the power ax is equal to a into e to the power ax. Now you see, this is the mathematical rule, this is the operator which after operation on this function gives the same function multiplied by constant quantity a. I repeat, when an operator operates on a function, produces the same function with a multiplied by a constant quantity a, then this function is called an eigenfunction. This is called an eigenfunction. And this constant quantity, this is called eigenvalue. I repeat, when an operator operates on a function, produces the same function multiplied by a constant quantity, then that function is called eigenfunction and the constant quantity is called eigenvalue, and this equation is called eigenvalue equation. Eigenvalue equation. Very simple. Eigenvalue, eigenfunction and eigenvalue equation. I repeat, when an operator operates on a function, produces the same function multiplied by constant quantity, then that function is called eigenfunction and the constant quantity is called eigenvalue, and this equation is called eigenvalue equation. Our next topic is addition of operators. So addition of operators is defined as suppose a cap and b cap are the two operators then addition of two operator is given by, that is, a cap plus b cap operates on a function fx equal to a cap fx plus b cap fx. So addition of operator is defined by this formula. Next, subtraction of operators. So subtraction of operator is defined as a cap minus b cap operates on a function fx giving the same result when fx minus b cap into fx. So addition of operator given by defined as like this, and subtraction of operator defined by this formula. Our next topic is product or multiplication of operator. It is the consecutive operation by two or more operators on a function. I repeat, the consecutive operation by two or more operator on a function is known as product or multiplication of operators. For example, let us consider two operators a cap and b cap. These are the two operators. So and fx is the operand. Therefore, multiplication of operator is defined as a cap, b cap, and fx. This means the function fx will first operated by b will give a result, and that result will be operated by a cap. That is the consecutive operation. First b produces one result, then by a. This is the multiplication of operator. That is, when b operates on function fx gives a result, say it is f dash x. So this is that is b cap when operates on fx gives f dash x. Now this f dash x will be operated by a cap, will give our final result f double dash x. So this is defined as multiplication of operator. Now, so in our simple algebra, you see 2 into 3 equal to 3 into 2. But in this case, a cap, b cap may or may not be equal to b cap or a cap. I repeat, our simple algebra 2 into 3 equal to 3 into 2. But in case of quantum mechanical operator, this is may be equal, may be correct, may not be correct. That is AB equal to BA may be equal, may not be equal. That is A cap B cap into Fx equal to B cap Fx A cap into Fx. If this is equal, if this simple operation is equal, then A and B, these two operators are commute to each other. If this is equal, if a cap fx, b cap, a cap fx, it is not equal, then a and b are not commute to each other. Let us take an example. Say a cap x our ddx and b cap is the multiplication of x. Multiplication of x. So let us, fx is the operand. Fx is the operand. Now a cap, b cap, fx equal to, we can write a cap means ddx, and b cap means multiplication of x, and what is our, that is function is fx. Now what is the result of this? This ddx of x into fx. So first is a product rule, we have to apply product rule, equal to first into ddx of second, that is f dash x, plus second into ddx of first, this is ddx of x equal to 1. Again b cap, a cap, f dash is equal to, what is bx, what is a ddx. Now what is our operand fx? So this is equal to x into, this is what, f dash x. Now you see a cap, b cap, fx equal to this formula, but b cap, a cap, fx equal to only this is. Therefore a cap, b cap, that is here we can say here a and b, that is ddx and our multiplication of x are not commute to each other, that is ddx and multiplication of x are not commute to each other. See your result are not here. This is the result for a cap and b cap, and this is the result for b cap and a cap. So these are not commute to each others. Now a commutator operator. Now with the help of these two operators, a cap and b cap, with the help of this two operators, we can construct a new operator. With the help of these two operators, we can construct a new operator which is written as a cap comma b cap, this is, which is equal to a cap, b cap minus b cap and a cap, or simply it is a cap minus b a. So this is called a commutator operator, which is called commutator operator. Now when a and b are commute to each other, commute to each others. Therefore a cap b cap equal to minus a cap equal to 0, or a cap b cap equal to b cap a cap. So this is all about commutator operator. So our next topic is linear and non-linear operator. For example, let us understand with an example. Suppose root over 4 plus 9 is not equal to root over 4 plus root over 9. I think you have understood this. This is root over 13 is not equal to, this is root is 2 plus this is 3. These are not equal. That is, see, root over, it is an operator. Why it is an operator? See, root over 9 is equal to 3. That is, root over changes this function to a new function. So root over is an operator. Now see, this root over of this operator, this root over operator operates on sum of two functions 4 and 9. Imagine these are two functions. Root over operates on two functions, give a result which is not equal when this operator, when the root over operates on the function separately. See here, this operator operates the function separately, produces the result which is not same when this operator, root over operator, operates on the sum of two functions. That's why when this is not equal, there is operation by operator on to sum of two functions is not equal when operation done separately, then such operators are called non-linear operator. So root over is non-linear operator, but when it is equal, it is a linear operator. So suppose a cap is an operator, is an operator is an operator, and f and g are the operand, Therefore, if a cap operates a sum of two functions f plus g, give a result when operation done separately. That is, when operator operates sum of two functions gives the same result when operation done separately, then A is a linear operator. A is a linear operator. If a cap is a function of operates on f plus g is not equal to a cap function plus a cap g, therefore a cap is not linear, that is non-linear operator, is non-linear operator. I think you've understood. So what is the example? Say example ddx. Here example ddx is a linear operator. ddx is a linear operator. So you can prove it directly. Say operator a cap is our ddx, okay, and let us take two operand. Say one is operands are, say, take any example. Say one is, say, x square, another is, say, operator, say our f equal to x square and g equal to, say, twice x, for example, twice x. Now a cap, our, say, formula f plus g equal to what, ddx of say it is x square plus twice x. So what is the result? Result is twice x plus 2. Twice x plus 2. Now individual, say f equal to, that is your ddx of x square, ddx f means x square equal to twice x, and a cap g, that is ddx of g means twice x equal to 2. Therefore a cap f plus a cap g equal to twice x plus 2. So twice x plus 2, twice x plus 2. So sum, this is the same. So ddx is a linear operator. Our next topic is Hermitian operator. This is a very important in quantum chemistry, the Hermitian operator. So let us understand Hermitian operator. An operator A will be Hermitian if it satisfies the following condition. An operator A will be Hermitian if it satisfy the following condition. That is integration of psi star a cap psi d tau is equal to integration of, say, psi a cap star psi d tau. This is the condition. When an operator A satisfies these conditions, then A will be Hermitian operator. Let us take another condition, same, suppose two different functions. Integration of psi 1 star a cap is psi 2 d tau equal to integration of, say, a psi 1 star psi 2 d tau. Say when an operator satisfy these conditions, then this operator is called an Hermitian operator. Now Hermitian operator has two very important theorem. Theorem number one, theorem 1, that is eigenvalues of Hermitian operators are real. Remember, eigenvalues of Hermitian operators, eigenvalues of Hermitian operators are real. So this word real, remember this question asks frequently in exam. Prove that eigenvalues of Hermitian operators are real. So let us prove this. Solution. Let us prove this. Let is an Hermitian is an Hermitian operator. Hermitian operator. Let psi is an eigenfunction, is an normalized eigenfunction. Normalized eigenfunction with eigenvalue A. So what is select? Psi is a normalized wave function of the operator A with eigenvalue A. So now apply eigenvalue equation. We can write the eigenvalue equation. What is the eigenvalue equation? Eigenvalue equation. What will be the eigenvalue equation? A cap psi is equal to A psi. Equation number 1. This is our eigenvalue equation. This is the eigenfunction, eigenvalue operator. Now let us take complex conjugate of this. Taking complex conjugate of equation 1. Let us take complex conjugate of equation 1. What we will get? A cap star psi star equal to A star psi star. Equation number 2. Okay. Now equation 1 multiply by psi star. Equation 1 is multiplied by psi star and integrating over whole space. So equation 1 multiplied by psi star. What do we get? Psi star. Psi star means complex conjugate of psi. A cap psi equal to, say, A is a constant, psi star psi. So multiplied by psi star. Now integrate it over whole space. So let us integrate d tau, say constant quantity, integrate d tau. Similarly, multiplying equation 2 by psi and integrating over 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 the whole space, of configuration. We get, so multiply equation 2, this is equation 2 multiplied by psi. So what we will get? First psi a cap psi star equal to a star psi into psi star. Now integrating d tau, so integrating d tau. So equation number 3 and this is equation number 4. Now already we know our A is a Hermitian operator. Since Hermitian operator, since the condition of Hermitian operator is satisfied, so in A, in this here A is not complex, but here say A is complex. So this left hand side of equation 3 and 4 equal. Left hand side of equation 3 and 4 equal because A is Hermitian, therefore right hand side should be equal. Since A is Hermitian, therefore LHS of equation 3 and 4 are equal. Therefore right hand side should be equal, so we can write A psi star psi d tau equal to A star psi star d tau. Now you see, since psi is normalized, so since normalized, so this should be equal to 1. Okay, psi is normalized, this should be equal to 1. Therefore A cap, so A star equal to A star. Since psi is normalized, I repeat, since psi is normalized, this should be equal to 1. This should be equal to 1 since psi is normalized, therefore A equal to A star. That is, A star is a complex conjugate. Whatever you take the complex conjugate should be real. That is, eigenfunction, that is eigenvalues of Hermitian operator are always real. Always real. Our theorem number 2 is, suppose there are two eigenfunctions of an operator. So let us understand with an example. Suppose psi 1 and psi 2 are the two eigenfunctions of the operator A cap having different eigenvalues. Psi 1 has eigenvalue A1, psi 2 has eigenvalue A2. That is, two eigenfunctions of the operator A cap having different eigenvalues, then these two functions are orthogonal to each others. That is, eigenfunctions, that is two eigenfunctions of an Hermitian operator, two eigenfunctions of an Hermitian operator A cap having different eigenvalues are orthogonal to each other. See, the two eigenfunctions of a Hermitian having different eigenvalues. I repeat, two eigenfunctions of an Hermitian operator having different eigenvalues are orthogonal to each others. So this is the theorem number 2. Two eigenfunctions of an operator A cap having different eigenvalues, then this psi 1, psi 2 are orthogonal to each others. So let us prove it. So what is the conditions we have seen here? The psi 1, psi 2 are the eigenfunction of the Hermitian operator A cap having eigenvalue A1, eigenvalue A2. So we can write first, say A cap psi 1 is equal to A1 psi 1. So equation number 1. Similarly, A cap psi 2 A2 psi 2, equation number 2. Let us take taking complex conjugate of equation 2, we get conjugate. Let us complex conjugate of this, we get A cap star psi 2 star equal to A2 star and psi 2 star, equation number 3. Now multiplying this equation, multiplying equation 3 by psi 1 and integrating over whole space of configuration, we get say psi 1 A cap star psi 2 star is equal to 2. So remember here again, see here one thing. So equal to, we can write A2 star equal to A2 star equal to A2 psi 2 star, equation number 3. Why? Because we know, just now we have proved A equal to A star. So A2 star equal to A2. So we can write A2 multiplied by psi 1, and we have to integrate, so let us keep some space, equal to A2 psi 1 psi 2 star. So multiplied by psi 1, now integrating d down, say integrating d down, so equation number, it will be 4. Now multiplying, say equation number 1, by psi 2 star, multiply equation 1 by psi 2 star and integrating same, and integrating. So let us multiply by psi 2 star. So this is psi 2 star A cap psi 1, keep sums equal to A1 psi 2 star psi 1. Now integrating d down, so equation number 5. Now you see, since A is Hermitian, so this is the Hermitian. See, the condition of Hermitian is satisfied. See, A psi 1 same. See here psi 2 star is complex. Here the psi A star become complex. So left hand side equal, since A is Hermitian. Since A is Hermitian, A is Hermitian, therefore LHS of equation 4 and 5 must be equal, is equal, is equal. Therefore right hand side should be equal. The right hand side, what is the right hand side? A2 star psi 1 psi 2 star d tau equal to A1 psi 2 star psi 1 d tau. Now this two common, psi 2 minus A2 minus A1 in integration psi 1 psi 2 star d tau equal to 0. Now you see this equal to 0 or this equal to 0, but a minus a1 not equal to 0, because already you have seen having different eigenvalue. A2 and a1 are not equal, so this must be 0. Therefore integration of psi 1 psi 2 star d tau should be 0. So which is not the condition of orthogonality? So this is the condition of orthogonality. Therefore psi 1 psi 2 are orthogonal to each other. So we have proved that two eigenfunctions of an Hermitian operator having different eigenvalue are orthogonal to each other. So I think you have understood what is an operator, what is Hermitian operator. Very important Hermitian operator, because in quantum mechanics all operators should be Hermitian, linear Hermitian operator. So thank you for watching this video.